11:02 in the morning, November 7, 1940. A 2,800-foot suspension span over Puget Sound twisted itself into a shape steel is not supposed to make and dropped 195 feet into the water. It had been open to paying traffic for 129 days. Somebody was filming. That's why you've seen it. The roadway rolling like a ribbon, a man crawling away on his hands and knees. And it's why you've probably been handed the cause. Gusts of wind matched the bridge's natural frequency, and resonance shook it apart. That explanation is sitting in physics textbooks right now. It's also wrong, and engineers have said so in print since 1991. Here's the detail that should have tipped everyone off. The bridge was designed to stand in winds of 120 miles an hour. It fell in 40. This is the forensic file on Galloping Gertie, the first Tacoma Narrows bridge in Washington state. We're going to take the famous answer apart using the actual numbers, then hunt the assumption hiding underneath it. A bridge that worked perfectly on paper and behaved like a wing over the water. Resonance is the playground swing. Push at exactly the rhythm the swing already wants, and small pushes become big arcs. Lovely idea. But it needs a metronome out there in the wind, and the usual candidate is vortex-shedding, air peeling off the deck's flat side in a steady alternating beat. So do the arithmetic. For Gertie's 8-foot deep girder in a 40-mile-an-hour wind, that shedding rhythm works out to roughly 1 beat per second. Now the bridge itself. The twisting motion that destroyed her cycled about 14 times a minute. Call it a fifth of a cycle per second. Those two numbers aren't close. They're about 2 octaves apart. Whatever the wind was doing to that deck, it was not keeping time with it. 2 engineers, Yusuf Billah and Robert Scanlan, laid this out in the American Journal of Physics in 1991, and they were blunt about it. Forced resonance and what actually happened to this bridge, they wrote, are fundamentally different phenomena, physically and mathematically, which leaves us with a much better question than the one the textbooks answer. If nothing was pushing the bridge in rhythm, then what tore it apart? Follow that back to a drawing office in New York. 1938, Clark Eldridge, bridge engineer for the Washington State Highway Department, has a design ready. A conventional suspension span stiffened by trusses 25 feet deep beneath the roadway. Deep, heavy, and open, so wind blows straight through the lattice. His estimate, about $11 million. Federal money came with strings. The Public Works Administration would fund a big share, but it wanted a bigger name on the superstructure. That name was Leon Moisseiff of New York, consultant on both the Golden Gate Bridge and the George Washington Bridge, and one of the most respected suspension engineers alive. Moisseiff had a theory, and it was genuinely cutting edge. In 1933, with Frederick Lienhard of New York's Port Authority, he published work showing that a suspension bridge's main cables, acting through the vertical suspenders, could absorb up to half the sideways wind pressure and shed it into the towers and anchorages. If the cables carry the wind, the deck doesn't have to, so Eldridge's 25-foot trusses became solid plate girders 8 feet deep, and the estimate dropped by roughly $4 million. Read the proportions that produced. 39 feet wide, 2,800 feet long. A width-to-span ratio of 1:72. The Golden Gates is 1:47. Depth to span here was 1:350, where the slenderest bridge previously built managed 1:84. And every calculation checked out for the load it was checked against. In that arithmetic, wind only ever pushed. Nobody asked what it might lift. The steelworkers found out first. Before the deck was even finished, the span was rippling in ordinary breezes, long, slow waves traveling the center span like a shaken rope. They called her Galloping Gertie. It was a joke around the site. It was also the first data point. July 1st, 1940. Bands played a march written by the Gig Harbor postmaster. More than 2,000 vehicles crossed on opening day, and the toll booths took in $11,541. A single-day record for that crossing that would stand for the next 14 years. Gertie kept galloping, and people paid to feel it. Some drivers detoured to avoid the seasickness, others queued up for the ride. In 4 months, the number of vehicles that crossed came to 265,748, more than the ferries had carried in all of 1939. The Toll Bridge Authority tried everything it could think of. Cables tying the deck down to 50-ton concrete blocks. They snapped. Inclined stays from the main cables to mid-deck. No real effect. Hydraulic buffers at the towers to soak up the motion. Their seals were ruined when the bridge was sandblasted for painting. Then they hired Professor Frederick Burt Farquharson, a civil engineer at the University of Washington, to put the bridge in a wind tunnel. He and his students built a model at 1 to 200 scale, and in that tunnel, occasionally, the model would stop bouncing and start to twist. Farquharson later told reporters what they'd said, watching it happen in miniature. If that sort of motion ever occurred on the real bridge, it would be the end of the bridge. His recommendations went in on November 2nd, cut holes in the girders or add fairings. The steel was ordered. November 7th, wind funneling across the Tacoma Narrows, that's the strait, not the city of Tacoma, steady around 40 miles an hour, gusting past that. The deck was heaving in the familiar way, and the familiar way had never hurt anybody. Just before 10, the bridge was closed to traffic. Shortly after 10, something small happened. A cable band at mid-span on the north main cable slipped along the cable, leaving that cable divided into 2 unequal lengths. The deck's motion changed character entirely. It stopped rolling up and down, it started to twist. Engineers on shore estimated the roadway's edges rising and falling 28 feet, rotating through 45 degrees, and doing it once every 5 seconds. One lane climbed, while the other dropped away. If you'd been standing at the center line, the far curb was moving through nearly 3 stories. Leonard Coatsworth, news editor at the Tacoma News Tribune, had driven on before the closure in his 1936 Studebaker. In the back seat was his daughter's black cocker spaniel, Tubby, a dog struck by a car years earlier who'd never fully recovered from it. Coatsworth lost control, braked, and was thrown onto his face against the curb getting out. He went back for the dog. The terrified animal bit him. So he crawled 500 yards to the tower on hands and knees, gripping the concrete curb, arriving on shore bleeding. 3 more men went out for that dog. Photographer Howard Clifford and reporter Bert Brintnall from Coatsworth's own paper, and Farquharson himself, who was there with his cameras running. All 3 had to turn back. By the state's own reckoning, the professor was the last man off Galloping Gertie. Around 10:30, a floor panel let go and fell 195 feet into the water. At 2 minutes past 11, the center span tore loose from the cables and went in. By 11:10, it was finished, and the hardest question of the whole affair was only starting. Here's the mechanism. Twist that deck even slightly, and the airflow separates off the flat face of the 8-foot girder, generating lift on the rising edge. Crucially, the timing of that lift is set by the bridge's own motion, not by the wind. Every cycle, it pushes the twist further. Engineers call it torsional flutter, or negative damping. A well-behaved structure bleeds energy out of its own movement. This one harvested energy from the wind in proportion to how hard it was already moving. Same instability that flogs a loose strap on a truck. Same instability that tears a wing off an airplane. So the unexamined assumption was never a number. It was a category. Mosaif's theory treated wind as a static sideways pressure, and about that pressure it was correct. Aerodynamic stability simply wasn't on the checklist, because for bridges in 1938, no such checklist existed anywhere. The board appointed by the Federal Works Agency, Othmar Ammann, Theodore von Karman, and Glenn Woodruff, reported on March 28, 1941. Their verdict placed the fatal weakness in the deck's extreme flexibility, vertically and in torsion. Not the steel, not the workmanship, the shape. Now, what's settled and what isn't? The self-exciting torsional mechanism is accepted, but how much vortex shedding contributed in the opening minutes, and how decisive that slipped cable band really was, are still argued in the technical literature. papers published within the last few years included. That's an honestly open question. The footage misleads too. Barney Elliott and Harbin Monroe, who ran the camera shop in Tacoma, captured it on 16mm Kodachrome. Elliott shot at 16 frames a second. The newsreels printed it at 24. So the gallop runs about half again too fast. The real thing was slower, heavier. Tubby was the only life lost that day. The Toll Bridge Authority eventually paid Coatsworth $450 for the car and $364.50 for its contents, the dog included. What he said stayed with him wasn't the bridge, it was telling his daughter. Clark Eldridge, whose deeper, costlier design had been set aside, took a Navy posting on Guam in 1941 and spent 3 years and 9 months as a prisoner of war in Japan. In the camp, an officer who'd studied in America recognized him and said 2 words, Tacoma Bridge. Leon Moisseiff's career ended with the span. He died in 1943, aged 71. His professional colleagues formally exonerated him, and the American Society of Civil Engineers named an award in his honor. David Steinman, another great bridge designer, put it as plainly as anyone. The entire profession shares in the responsibility. He was right. 4 months after the collapse, Columbia's Professor J.K. Finch cataloged a century of forgotten wind failures. The Brighton Chain Pier in 1836, Wheeling in 1854, Niagara Clifton in 1889. Nothing about Gertie's behavior was new. It had simply fallen out of the profession's memory. What her failure built. Wind tunnel testing as standard practice for long spans. A replacement sturdy Gertie opened in 1950 on Eldridge's original piers with a 33-foot open stiffening truss and wind grates in the deck. In 1953, the Golden Gate Bridge was let a stiffening contract worth over $3 million. And the center span is still down there, more or less where it landed. In 1992, the wreckage was placed on the National Register of Historic Places, part history, part shield against salvagers. 8 decades of barnacles later, it's counted among the largest artificial reefs on Earth. Galloping Gertie didn't fail because somebody got the arithmetic wrong. She failed because a generation of engineers had forgotten how to ask a question, so she asked it for them at 2 minutes past 11 in the morning on color film. If you're like us and you appreciate stories like this one, give us a like and a follow. It really helps the channel and we greatly appreciate it. And as always, stay curious, stay careful, and remember, every failure is a lesson somebody paid for.